On the fog-drenched plains of Lorraine in September 1944, the Sherman tank was still viewed as the fragile underdog of Allied armor. Facing the German Panther, equipped with sloped 80mm frontal armor and a deadly high-velocity 75mm KWK-42 cannon, American tank crews often entered battle with grim acceptance of mechanical inferiority. The Sherman's standard 76mm armor-piercing rounds failed repeatedly against the Panther's frontal plate, forcing desperate flanking maneuvers that cost time, lives, and machines. Yet deep within American ordnance laboratories, scientists and metallurgists had quietly produced a weapon that would rewrite armored warfare. The M93 high-velocity armor-piercing round, nicknamed HVAP, by those who tested its astonishing potential under strict secrecy. Its secret lay within its heart, a tungsten carbide core housed in a lightweight aluminum alloy shell, a combination that generated incredible muzzle velocity, exceeding 1,000 meters per second. In ballistic tests at Ardennes Proving Ground, the HVAP achieved armor penetration exceeding 160 millimeters at 1,000 yards, outperforming every previous 76mm shell ever fielded. American engineers realized they had turned raw material science into battlefield supremacy. When loaded into the Sherman's 76mm gun, the round produced a bright silver flash that inspired its battlefield nickname, the Silver Bullet. Tank commanders first received these limited rounds during the Lorraine campaign, where Lieutenant Colonel Creighton Abrams' 37th Tank Battalion faced waves of German armor near Arracourt. As dawn broke through misty September air, HVAP rounds ripped through Panther hulls once thought untouchable, shocking enemy crews who believed Allied firepower could never breach their steel confidence. What followed was a sudden reversal of fate. American tankers, once cautious hunters, became relentless predators across the rolling French countryside. Whispers of these miraculous shells spread quickly across armored divisions, transforming morale and tactical doctrine overnight. For the first time, the Sherman no longer symbolized industrial compromise, but mechanical ingenuity, overcoming German superiority through innovation rather than size. Inside the laboratories of Watertown Arsenal and Frankfurt Ordnance, American metallurgists confronted a challenge no less formidable than any battlefield commander. The task was not to design a heavier projectile, but to engineer one that could defeat German steel through velocity and density alone. Tungsten carbide became the solution, a compound so hard it could slice through armor without deforming, maintaining structural integrity even under the immense heat and pressure of high-velocity impact. This innovation required precision manufacturing beyond anything previously attempted in mass wartime production, forcing factories to refine casting methods and quality control to microscopic tolerances. Unlike traditional steel-capped armor-piercing shells that relied on brute force, the HVAP achieved lethality through kinetic focus. Engineers calculated that by reducing overall projectile weight while concentrating tungsten density at the tip, they could achieve muzzle velocities exceeding 1,036 meters per second. This speed generated armor penetration exceeding 160 millimeters at 1,000 yards, enough to pierce the frontal plate of a Panther or Tiger under favorable angles. Yet every scientific triumph carried logistical consequences, for tungsten was among the rarest strategic materials available to the Allies, sourced primarily from Chinese and Bolivian mines, guarded fiercely against Axis acquisition. The War Production Board rationed tungsten like gold, allocating only limited quantities for priority weapons research, while urging engineers to find substitutes that never matched its performance. Each HVAP round therefore represented both technological mastery and resource sacrifice, a single bullet forged from global coordination across continents and laboratories. Ballistic testing at Aberdeen and Fort Knox confirmed extraordinary results, recording penetrations previously thought impossible from medium tank calibers. Reports soon reached the European theater headquarters, and by early autumn 1944, limited shipments were dispatched to frontline armored divisions. Tank crews receiving them treated each round as a rare treasure, often saving them for critical ambushes or duels against Panthers threatening column movements. What began as an experimental metallurgical project now stood poised to redefine tactical balance across France, proving that material science could achieve what sheer firepower could not, transforming a humble 76mm gun into a precision instrument of industrial warfare. On the fog-drenched morning of September 19, 1944, the rolling fields around Arracourt concealed two armored forces groping blindly for advantage. Lieutenant Colonel Creighton Abrams' 37th Tank Battalion, equipped with 76mm Shermans, faced elements of Germany's 5th Panzer Army, advancing with confidence in their Panther superiority. The engagement would become the proving ground for America's newest secret, the M93 HVAP round, and the battle that redefined the Sherman's reputation. Visibility dropped to less than 100 yards, forcing combat into sudden, violent encounters where first shots decided survival. Abrams gunners, trained to identify silhouettes through mist and muzzle flash, began loading their scarce tungsten-cored ammunition with deliberate precision. When the first HVAP shell left its barrel, it struck a Panther's frontal plate and penetrated cleanly, erupting in flames that stunned nearby crews. The American tankers, accustomed to deflection and ricochet, watched in disbelief as the tungsten core carved through German armor like glass. Word spread across radio channels with excitement and urgency. The new rounds punched through them, transforming cautious defense into aggressive pursuit. Within hours, Panthers that once commanded respect became burning silhouettes across the Lorraine fields, their commanders struggling to comprehend how Sherman suddenly possessed such devastating reach. German after-action reports described confusion and disbelief, citing impossibly high-velocity impacts and armor failure under unexpected penetration angles. For the first time, numerical inferiority did not translate into tactical disadvantage. Abrams' men exploited mobility, fog, and their few HVAP shells to devastating effect, ambushing advancing Panzer formations from flanking positions before retreating into concealment. Each hit reinforced the psychological reversal that American crews long awaited. The hunters had become the hunted. By dusk, radio intercepts confirmed catastrophic German losses. 86 enemy tanks lay destroyed or abandoned, while 25 Shermans were lost in return. Arracourt was no longer a simple defensive victory. It became empirical proof that innovation in industry could conquer mechanical superiority. The tungsten penetrator, born in secrecy and scarcity, had altered armored warfare's hierarchy overnight. What followed in the coming weeks would prove even more profound. The recognition among Allied command that science, not size, now determined victory in modern mechanized war. Behind the front lines, the victory at Arracourt ignited an invisible conflict fought not with tanks or guns, but with raw materials and mathematics. Tungsten, the essential element powering every HVAP core, suddenly became the most coveted metal on Earth. Its density, resilience, and ability to maintain hardness at extreme temperatures made it irreplaceable, yet its sources were perilously limited. The United States depended heavily on imports from China's Jiangxi province and Bolivia's Oruro mines, both vulnerable to disruption by Axis intelligence and shipping attacks. To sustain production, Allied procurement officers waged a silent campaign of diplomacy, espionage, and economic pressure to secure every available ounce. Factories at Frankfurt Arsenal, Remington Arms, and General Motors' Saginaw plant raced to convert tungsten into armor-piercing penetrators, but production quotas never met field demand. A single ton of tungsten yielded only a few thousand HVAP rounds, forcing commanders to allocate them with surgical precision. In some battalions, gunners received as few as 5 per tank, reserved exclusively for confirmed heavy armor contacts. Each round fired was a decision weighed between immediate necessity and strategic conservation, creating a tension unknown in conventional ammunition supply. Meanwhile, German metallurgists, aware of tungsten's power, attempted to divert neutral Portuguese exports through covert trade networks, offering gold and industrial machinery in exchange. Allied intelligence intercepted shipments, launching Operation Blockade Mineral, a coordinated effort to sever Axis access to high-density metals. By 1944, Germany's tungsten stockpiles had dwindled to critical levels, crippling production of its own armor-piercing ammunition and precision tooling. The material war became as decisive as any battlefield engagement, shaping outcomes far beyond artillery range. Engineers warned that without tungsten, HVAP programs might cease altogether by winter. In response, the U.S. government classified tungsten as a critical strategic resource, second only to uranium. Experimental substitutes using depleted uranium, hardened steel, and tungsten iron composites failed to achieve comparable performance. Despite shortages, small shipments continued reaching armored divisions in France, sustaining morale and tactical superiority even as scarcity loomed. The Tungsten War illustrated a fundamental shift in 20th century conflict. Industrial chemistry had become strategy, and logistical mastery had replaced heroism as the key to survival. What began as an engineering experiment had now evolved into a geopolitical contest of extraction, transport, and endurance, where every bullet told a story of science overcoming scarcity. By October 1944, as Allied forces pressed deeper into Lorraine and beyond, General Dwight D. Eisenhower found himself confronting a paradox of success and scarcity. Reports from the 12th Army Group celebrated the astonishing effectiveness of the 76mm HVAP round, yet the very weapon that could shatter German armor remained in critically short supply. Eisenhower's correspondence with the War Department revealed increasing frustration, not with his commanders, but with an industrial system strained by material bottlenecks. He understood that battlefield victories depended not merely on courage or coordination, but on the continuous flow of tungsten through ships, trains, and factories thousands of miles away. Creighton Abrams' after-action summaries from Arracourt emphasized how HVAP rounds changed morale and tactical tempo, yet their scarcity forced tank units into dangerous improvisation. Many crews entered engagements carrying only 2 or 3 tungsten shells per vehicle, supplementing with standard armor-piercing rounds that could barely breach Panther side armor under optimal conditions. The result was a battlefield defined by calculated restraint, where gunners held their fire until absolutely certain of both range and target identity. Commanders debated whether limited HVAP stockpiles should be centralized for decisive operations or distributed evenly across armored formations to maintain psychological balance. Eisenhower, ever pragmatic, sought immediate production increases, pressing ordnance to prioritize tungsten for frontline ammunition over industrial tooling. Yet the metallurgical demand of aircraft engines, precision lathes, and artillery fuses competed for the same element, and shifting allocations risked crippling other critical manufacturing chains. Field officers continued to send urgent requests through logistical channels, pleading for the weapon that could level the battlefield against German armor. In one notable message dated November 2nd, Eisenhower described tungsten as the battlefield equivalent of oxygen, a poetic yet painfully accurate metaphor for the dependency of modern mechanized warfare on industrial chemistry. Strategic decisions now extended beyond maps and troop dispositions into the realm of raw material economics. As 1944 drew to a close, the 76mm HVAP had proven itself tactically decisive but strategically constrained, a weapon of immense potential limited by geological scarcity. The lessons were unmistakable. Even the finest engineering triumphs required sustainable resources, and without them, technological superiority risked becoming a fleeting illusion under the relentless weight of war. When word of the HVAP round's devastating performance reached German Panzer regiments, disbelief turned swiftly into dread across the armored corps. Reports from the Lorraine front described Panthers destroyed from frontal engagement ranges previously considered safe, their armor punctured by unseen projectiles that struck with unearthly velocity. Commanders initially dismissed such claims as exaggeration, yet field inspections revealed circular entry holes without deformation, evidence of tungsten-cored penetrators slicing clean through hardened steel. For crews accustomed to invincibility behind 75mm of sloped armor, the illusion of superiority vanished overnight. Panzer units that once advanced confidently under Allied fire began adopting defensive postures, maneuvering cautiously and avoiding open terrain. Veteran gunners whispered rumors of a new, phantom ammunition, capable of piercing even the vaunted Panther glacis, a psychological tremor that spread faster than any technical analysis could contain. Allied tactical radio intercepts recorded intercepted chatter filled with apprehension and disbelief, reflecting a morale collapse unseen since the early defeats of 1941. German commanders ordered increased use of hull-down positions and ambush tactics. Yet even these offered limited reassurance when tungsten shells appeared capable of striking through both frontal armor and engine compartments with surgical precision. Captured crew diaries later revealed the deep mental toll inflicted by this new threat. Tankers described sleepless nights, listening to the echo of impacts that once bounced harmlessly, now detonating catastrophic explosions inside their vehicles. The battlefield became an environment of uncertainty, where numerical superiority or tactical discipline could no longer guarantee safety. The confidence once drawn from superior engineering gave way to fatalism, a quiet recognition that industrial disparity had outpaced battlefield skill. The HVAP's effect extended far beyond material destruction. It altered perception itself. German tankers began overestimating American firepower, withdrawing prematurely or abandoning positions at the first sign of coordinated attack. This psychological erosion magnified Allied success far beyond what logistics alone could explain. War correspondents and intelligence officers noted a marked decline in German aggressiveness, describing engagements where Panther platoons retreated before contact, unwilling to test fate against what they believed were unstoppable munitions. By the winter of 1944, the Panzerwaffe's battlefield spirit had fractured. Fear of tungsten penetrators, small, scarce, and silent, had achieved what countless artillery barrages could not: the destruction of German confidence in armored supremacy. As the bitter European winter settled upon the scarred landscapes of eastern France, the lessons of Lorraine began shaping Allied operational doctrine across the Western Front. Reports from Creighton Abrams battalion reached higher command echelons, transforming individual tactical experiences into institutional knowledge, guiding armored warfare through the final campaigns toward the Rhine. The HVAP round, once experimental, now symbolized America's fusion of scientific precision and industrial adaptability, a combination Germany could neither match nor counter through field innovation. By December 1944, shipments of 70-cm HVAP ammunition arrived sporadically at forward depots supporting Patton's Third Army, where distribution required careful tracking under Eisenhower's strict material rationing protocols. Tank crews crossing into Luxembourg and Belgium during the Ardennes offensive carried their tungsten rounds like relics, marking crates with chalk initials to ensure none were misplaced. When German armor surged during the Battle of the Bulge, those same scarce shells became decisive in halting armored thrusts along the frozen ridges near Bastogne and Majoret, where every penetrative shot restored faith in the Sherman's resilience. Allied gunners, now familiar with the HVAP's ballistics, learned to exploit its velocity advantage through disciplined range estimation and predictive targeting, often engaging at ranges once deemed futile. Combat reports documented Panther and Tiger tanks neutralized at distances exceeding 1,000 meters, feats unthinkable earlier that summer. Each engagement underscored an evolving warfare principle, that industrial science could compensate for engineering inferiority, and that battlefield supremacy depended less on design philosophy than on material ingenuity sustained by mass production. For the Germans, the transition from dominance to desperation accelerated. Their factories, crippled by bombing and mineral shortages, struggled to maintain even standard ammunition output, let alone develop equivalents to the tungsten-cored penetrators devastating their armored spearheads. Commanders lamented in post-war interrogations that the Americans had found a bullet that no steel could stop, a testament not merely to technological shock, but to the psychological acknowledgement of industrial defeat. By February 1945, as Allied armor breached the Siegfried Line and closed upon the Rhine, the 70-cm Sherman, long dismissed as undergunned, had become a symbol of adaptive warfare. Its effectiveness was not measured solely in penetrations or kills, but in how it demonstrated that intellect, coordination, and chemistry could overcome any numerical or mechanical disadvantage. Beneath the roaring machinery of Detroit's assembly lines and the humming furnaces of Bethlehem Steel, America's wartime miracle achieved its purest expression in tungsten-cored precision. The M93 HVAP round stood not merely as an engineering marvel, but as the living proof that modern warfare had evolved into a contest of production tempo, scientific mastery, and logistical orchestration. Each shell represented a synchronized achievement across hundreds of factories, laboratories, and transport convoys linking continents in pursuit of material dominance. The triumph at Arracourt had shown that battlefield ingenuity depended entirely upon industrial endurance, the power to convert abstract metallurgy into battlefield consequence at scale. Throughout 1945, U.S. industrial statistics revealed astonishing contrasts. While Germany produced fewer than 70,000 trucks, America rolled out 650,000, alongside 96,000 aircraft and 40,000 tanks. Each figure told a single truth. The Sherman's might was not confined to armor thickness or gun caliber, but multiplied through uninterrupted resupply. HVAP production epitomized that principle, fusing scientific creativity with manufacturing discipline that dwarfed every German effort. The tungsten shortage, though critical, never paralyzed the system. Rather, it spurred innovation, adaptation, and relentless pursuit of substitutes until victory was inevitable. War correspondents visiting U.S. ordnance plants described scenes resembling orchestras of precision, where machinists shaped penetrator cores with micrometer tolerances, guided by metallurgists who once built tools, now building victory. Behind them, convoys carried these small, dense symbols of industrial supremacy toward harbors feeding the European front. There, amid the roar of engines and the clatter of steel, the industrial miracle translated into battlefield transformation. Every round fired from a 76mm Sherman linked Detroit's engineers to Abrams's gunners, a seamless chain of intellect and courage uniting scientists, soldiers, and strategists into one mechanical organism of victory. When historians later dissected the reasons for Germany's collapse, they spoke less of tactical brilliance and more of industrial inevitability. The tungsten shell had become the material embodiment of American war philosophy. That technology's highest purpose was not innovation alone, but relentless, reproducible dominance. In the age of mechanized conflict, production itself had become the new strategy, measured not in courage or conviction, but in tons, volts, and velocity. When the guns finally fell silent in 1945, the tungsten cores that once shattered German armor began shaping a new era of scientific warfare. The lessons learned from the M93 HVAP program did not end with the fall of Berlin. They became the foundation for the next generation of kinetic energy weaponry. American ordnance engineers, freed from wartime urgency but not from curiosity, began experimenting with new materials and aerodynamic profiles, seeking penetrators capable of maintaining both velocity and stability at even greater ranges. The knowledge that dense metals could alter the balance of power between nations transformed weapons research into a permanent strategic endeavor. At Ardennes Proving Ground, test divisions conducted ballistic experiments inspired directly by HVAP successes, leading to the development of armor-piercing discarding sabot, APDS, and later armor-piercing fin-stabilized discarding sabot, APFSDS rounds. These designs carried forward the same principles: concentrated mass, minimal drag, and maximum kinetic energy, but with refined sub-caliber penetrators capable of piercing armor far thicker than any wartime tank. Tungsten, though scarce, remained the core material until the dawn of the atomic age introduced uranium alloys that extended both performance and controversy into the modern battlefield. The Korean War provided the first true post-war proving ground. American M26 Pershings and M46 Pattons, firing tungsten HVAP ammunition, achieved remarkable success against Soviet-supplied T-34-85 tanks, confirming that the tungsten advantage still reigned supreme. Reports from the Korean Peninsula described engagements echoing Arracourt, rapid penetrations, catastrophic enemy losses, and an enduring reminder that material science remained the decisive factor in armored combat. The experience reinforced U.S. military doctrine that research, production, and combat must function as an unbroken chain of innovation, ensuring technological continuity across generations. As the Cold War unfolded, The same metallurgical lineage evolved into the depleted uranium penetrators used by M1 Abrams tanks decades later, weapons whose ancestry traced directly to the tungsten rounds of 1944. The principles remained constant: velocity, density, precision, and adaptability, while the names and nations changed. The spirit of the HVAP lived on, embedded within every projectile that relied on physics rather than explosives to conquer steel. In laboratories, classrooms, and battlefields, the legacy endured. That industrial intellect, once awakened, could never again be confined to a single generation or a single war. In the decades that followed, historians and engineers alike came to regard the 76mm HVAP round as a symbol of industrial genius and scientific persistence under pressure. What began as a desperate wartime improvisation evolved into a lasting testimony to how intellect, cooperation, and production could rewrite battlefield reality. The tungsten penetrator, small in size but monumental in consequence, bridged the distance between laboratory theory and mechanized victory, proving that innovation thrives most when necessity narrows its path. The Battle of Arracourt, once obscure in Europe's vast theater of conflict, became the defining case study demonstrating that technology, not mythology, decides survival in modern war. German officers interrogated after the surrender described their shock not at Allied courage, but at the sheer precision of America's industrial orchestration. They had confronted a nation that fused science and labor into a single war-making system, where every factory worker indirectly commanded a battlefield. The Panther's steel, once feared, became brittle before tungsten's velocity, and in that moment, a new truth emerged. That strategy without material mastery is illusion. Each HVAP round fired had not merely pierced armor, it had punctured an entire philosophy that believed mechanical craftsmanship could outweigh economic might. For the men who fired those shells, the memory endured not as triumph, but as revelation. They had witnessed firsthand the transformation of warfare into a realm ruled by density, velocity, and calculation. Behind every impact lay the unseen hands of miners, metallurgists, machinists, and logisticians whose contributions formed the invisible backbone of victory. From the smelters of Pennsylvania to the laboratories of Massachusetts, their collective labor reshaped the moral geography of war, proving that innovation, when bound to discipline, could preserve lives by shortening conflict through overwhelming superiority. In the twilight of that industrial century, the tungsten core became more than ammunition. It became metaphor. It embodied the idea that progress, once harnessed to purpose, can alter not only outcomes, but understanding. As veterans aged and machines rusted into museum relics, the lesson remained luminous. That knowledge, not courage alone, defines endurance, and that the war for supremacy begins not on the battlefield, but in the forge where science meets necessity.